Hi everyone. In this video, I am going to introduce a different circuit design like RL circuit. Previously, we have seen RC circuits like low pass RC circuit and high pass RC circuit. But in this video, I am saying instead of capacitor, we can also use an inductor to make a low pass or high pass circuitry. Okay, that means the filter can be made up of any of these three components like RLC, because these three components are passive components which are used to design a particular filter, a high pass filter or low pass filter. Not only a pure capacitor and resistor, but a resistor and inductor can also make this particular connection like a low pass and high pass RC circuits. And RLC circuit is also there, which is also used for the filtering, but here the filtering will be done like with the help of both capacitor and resistor. Okay, most commonly used RLC circuits are for resonant circuits. Resonant circuits or ringing circuits, those are the applications of these RLC circuits. But when we consider RL and RC circuits, we can design a low pass and high pass circuits. Now, let us see how a low pass RL circuit is going to be designed. First, inductor is there, followed by resistor. This is the output. We are taking a cross resistor. Let us consider this as R dash and this is L. It is the place where we are applying the input voltage. Now, see here, I am saying this circuit as low pass RL circuit. Low pass RL circuit. Low pass RC circuit. Did you remember low pass RC circuit? How the structure will be? How the components are connected? Low pass RC circuit. First resistor and then followed by a capacitor. In the low pass RC circuit, we have taken the output voltage across capacitor. But in the low pass RL circuit, we are taking the output voltage across resistor. So simply replacing L and C is not at all sufficient. That will not give you the exact low pass RL circuit. Okay, I will draw that one also. Low pass RC circuit. Low pass RC circuit. It is a resistor followed by capacitor. Resistor followed by capacitor, and this is the place where we are taking the output voltage, and this is input voltage R and C. This is low pass RC circuit. This circuit is a little bit different compared to the RL circuit. Just the resistor is taken as a new resistor like R dash, just to show the difference between the low pass RC and low pass RL circuits. I am just taking a different resistor like R dash. You can use the same R, no problem, but here just to show that difference I have taken as R dash, and instead of C now we have to use L. Okay, suppose some may think that just by replacing the capacitor into inductor R followed by L, that makes RL circuit as a low pass RL circuit. That becomes high pass RL circuit. Don't do like that. Okay, so this RL circuit gives you low pass filter when construction is like this only. Inductor followed by resistor. Inductor followed by resistor. Okay, this constitutes low pass RL circuit. Similarly, high pass RL circuit, high pass RL circuit. High pass RL circuit, nothing but what is the construction of high pass RC circuit? Capacitance followed by resistor. But now here resistance followed by, opposite is the case, inductor. Resistance followed by inductor. So draw the resistor and inductors properly. So this is the output voltage V0 and this is input voltage VA. What I said, R dash and this is L. So in high pass RL circuit, we are taking the output voltage across inductor. I will draw the same high pass RC circuit. See, you no need to draw this high pass RC and low pass RC circuits in the examinations when you are asked about particularly RL circuits. Just I want to show you the difference between these two circuits. That's why I am drawing here. So high pass, what I told you, high pass RC circuit, nothing but your CR, which is having highest priority. So C followed by R. This is the circuit with respect to the high pass RC circuit. When we are taking high pass RL circuit, resistance must be followed by inductor L. This is the high pass RL circuit. Okay, now let us move on to RLC circuits. The behavior and operation and application is same with respect to the RL and RC circuits. Both are same. Okay, just I want to show you how the circuits are going to be constructed with the help of inductor. Now RLC circuits. RLC circuit. RLC circuit is nothing but, in this circuit totally three components are there: resistance, inductance and capacitance. Resistance, inductance and capacitance. Don't confuse, whatever the name we have written here, draw the circuit as per the names. First resistor is there, and then inductor is there, and then capacitor is there. So resistance followed by inductor followed by capacitor, but capacitor take it as like this. That means across capacitor we are taking the output. This is the output C, and this is L, and this is R. Here is the place where we are applying the input voltage. Let us consider they are varying with respect to time, and it is I of t, V naught of t. Okay, so now this particular RLC circuit is having applications like a ringing circuit or to calculate the resonant frequency of the circuit. Okay, resistance, inductance and then capacitance. It is also like a filter. RL, RLC, RC, all these are filters. LC, these are filter networks. Okay, whenever the combination of this capacitance or inductance comes into the circuit, definitely that particular network acts as a filter. Now let us calculate the output voltage and what are the different possible output waveforms that are coming from this particular RLC circuit. When a step input is applied, we will see. Okay, so let us write KVL around the loop. Then Vi of t is equal to R into I of t. We know very well how to write, plus how to write the voltage across inductor, L into di by dt plus 1 by C integral I of t dt. So simply we know, apply Laplace transform on both sides. Apply Laplace transform on both sides, then what happens? Vi of t becomes Vi of s, and R same I of s plus L into di of t by dt. Di of t by dt means s into I of s plus 1 by C integral I of t dt. Integration gives 1 by s I of s. So that is equal to Vi of s is equal to, write in capital, R into I of s plus L s I of s plus 1 by Cs into I of s. So take I of s common, and now R plus Ls plus 1 by Cs. Okay, so this is what the input voltage equation we can write. Okay, and more precisely, if you want, take I 1 by Cs as common, then simply it becomes LCS S square plus RCS plus 1. Just I have taken 1 by CS as LCM, and output voltage we are taking, and voltage across capacitor, nothing but, or we can say output voltage. Output voltage, how to write output voltage? V naught of S is equal to I of S plus 1 by, I of S into 1 by CS. I of S into 1 by CS. So the transfer function, therefore, the transfer function how to calculate transfer function? V naught of S by output voltage by input voltage, VA of S, that is equal to this one divided by this one. These two cancelled and we are left with 1 by LC S square plus RCS plus 1. For that purpose we have taken the CS as common and both factors are same, so we can simply write it as 1 by LCS square plus RCS plus 1. So take LCS common, that is equal to 1 by, if you take LC common, what happens here? The second order coefficient becomes 1. S square plus 1 by, it is R is there, R by L into S plus 1 by LC. So S square plus R by L into S plus 1 by LC. This is the transfer function V naught of S by V of S. Take the roots of this particular quadratic equation. Roots of this characteristic equation, how to write? How many roots will come? 2 roots will come, we know. Okay, x square plus ax square plus bx plus c, ax square plus bx plus c. Okay, you may know or remember this equation. So the roots of equation s square plus, whenever we are going to calculate the roots, we should equate that equation to 0. Okay, we know how to write these roots. Minus b, how many roots are there? Like r1, r2, 2 roots are there because it is a 2, order is 2. Minus b plus r minus square root of b square minus 4ac divided by 2 into a. Similarly, take 2 roots s1 and s2 is equal to minus b minus r by l. This is a1, b equal to r by l, and c is equal to 1 by lc, plus or minus square root of b square r by l whole square minus 4 into a is nothing but 1, c is nothing but 1 by lc, by 2a. 2 into a is nothing but 1 by 2. Just take this 2 also into the numerator factor, then it is minus r by 2l plus or minus square root of r by, see, when this 2 goes into this square it becomes 4, and again when it goes into this when it goes into the root it becomes 4, and when it goes into the square again it becomes 2. So r by 2l whole square minus, and when this 2 goes into this square root becomes 4, 4 gets cancelled and it is 1 by LC. These are the roots we are having, S1 and S2. Okay. Now, based on these roots, we can determine 3 different conditions. What happens when R by 2L is greater than 1 by LC, and R by 2L whole square is equal to 1 by LC, and R by 2L whole square is less than 1 by LC. Roots becomes positive and real, roots become complex, and the root becomes only minus R by 2L. If R by 2L whole square is greater than 1 by LC. See, what I have assumed is I have taken the same roots S1 and S2. If this root factor R by 2L whole square is greater than 1 by LC, what happens then? It becomes a positive value and the overall value will become a real value. That leads to R greater than root L by C multiplied by 2. Okay, R should be greater than 2 times of root L by C. Then what happens? The roots are real and we will be having different roots. The roots are real and different. The circuit is over damped and there are no oscillations in the output. The circuit is, I will draw the waveforms. The circuit is over damped and no oscillations. No oscillations. This is first condition. Second condition is if R by 2L whole square is equal to 1 by LC. That leads to R is equal to 2 times square root of L by C. What happens then? When these two values are equal, the second factor becomes 0 and you are only left with minus R by 2L. What happens? Roots are same and it is minus R by 2L. Okay, both roots are real and equal. So in this condition, both roots are real and equal. The circuit is critically damped. Here also there are no oscillations. We can say here also there are no oscillations. And the third condition, R by 2L whole square is less than 1 by LC. Then what happens? R is R is less than 2 times of square root of L by C. Then what happens? See here, when this particular factor is less compared to the negative factor, so root over we are having negative value, then I comes here. That is nothing but imaginary. The roots are imaginary. Then the roots are complex conjugate. Complex conjugate, or we can say it is imaginary roots. Then the circuit is under damped and there will be oscillations in the output. Circuit is under damped and oscillations are there. Okay, so when a step input is applied, see we are studying with respect to the step input. When step input is applied, what happens? Let us draw two different graphs. One is with respect to the current I of t and another one is with respect to the voltage. V0 and this is the input voltage Vi. Okay, step voltage V, and the current is also for overdamped. There will be a current flowing like this. I told you already this is acting as a resonant circuit. So we will be having maximum current at only one instant. This is for overdamped. We know the condition overdamped is nothing but R greater than 2 times of root L by C, and this is for critically damped. Critically damped, and oscillations are there in the underdamped condition. It is underdamped. Similarly, we can draw the output waveform also. Underdamped is having oscillations and it takes long time to stabilize. This is underdamped. And now critically damped, and this is over damped. Critically damped, over damped looks similar but with different amplitudes. This is critically damped and this is over damped. Okay, so this is the way how an RLC circuit behaves when a step input is applied, and it particularly acts as a resonant circuit. Okay, thank you.